All right, y'all. So let me explain a couple things. Oh, let me make sure I'm not muted. No, I'm not muted. Okay, let me explain a couple things. So we are about to start getting remote students back. Okay, so that's why there's an extra row. And there's still as space as possible, but I have one class that has 25. It's not this one. I think it's 73 that has 70. So because I know that there's really only 2 outlets here, and there's 1 outlet there. So I'm hoping I have 2 power trips at home. This is not the safest solution to our problem, but what I'm going to do is I'm going to feed one from back here around this corner, because you guys only have 1 outlet for all of you. That way you can plug in this power strip. And then these desks would essentially be sharing this one. And then this is dirt all over my floor. And then I'll do another thing over here. I'll feed it around the side. I can't even sit in the back. I'm so sorry. There's not enough human time in the universe for me to be able to sanitize everything at once. But then, and I have a power strip at home. I don't have 2, but I'm just going to feed one over here, because if you guys are both plugging here, then nobody else can use it. So I don't know how else to deal with this situation. Yes, somebody did test positive last week. Not one of my students, okay, but somebody somewhere on campus. No, I don't need to know the name. They don't tell us this on purpose. So because of the way that you guys are grouped, I have quite a few students that are now on 14-day quarantine because they were in, I don't know, it's not like they were spitting on each other or anything, but they were in close proximity with whoever the student was. And yes, I've got somebody that's in multiple classes. I got a chemistry kid, I got 6 or 7 first base kids that are now on voluntary quarantine, so self-quarantine. So, I don't know. It is what it is, and we're dealing with it. We're going to start getting remote kids back, and it's going to be absolute chaos, and we're just going to roll with the punches and figure stuff out. So if we're going to be moving around for seats, we've got to figure that out. But once we do that, we can't be flip-flopping around everywhere and going back and forth, because those have to be ready for me to be able to do labs. So yeah, it's lots of fun. Lots and lots and lots of fun. All right, for this focus, we've done this. We've introduced stars before. We're going to go more in depth today. Am I going to talk about every single type of star that exists? Nope. I will mention a couple. We'll talk about red dwarfs, and we'll talk about some of the supergiants. We'll talk about Wolf-Rayet stars. But I don't have enough time to go into every single subclass of star. There's 3 major classes of stars. They're average, they're massive, and they're supermassive. Yes, there are subsets in those. But those 3 types of stars, they are going to end their life in one of 3 ways. We've talked about this. How do stars end their lives? In what form? Because they don't all go boom. No, the after-planetary nebula for one of the 3. After the supernova for the other 2. Okay, so the massives, the smaller of the big ones, those neutron stars. What are the other 2 possible things? Black holes if they're really big. And then what else? Our star does this. White dwarf. And we haven't had enough time to see black dwarfs. So yes, they're hypothesized, they're theorized, and I'll talk about it a little bit, but we haven't found any. There hasn't been enough time. If you were not here yesterday, so that would be Aiden, because I need to figure out why you're there and you're not in here. Aiden, type in chat and let me know if you're going remote or if you're just not here. Dean, you weren't here yesterday, were you?
No.
Okay, so you missed the test. It's open, and I took the access code off it.
Okay, I was gonna take it yesterday, and I forgot to email you.
And I left the access code on until this morning. So, but it's okay now.
Okay.
You can take it. You only get 1 shot, so. Chris, where's Josh at? No. Does anybody still need this slide, or can you go forward? You go forward. I'm still taking attendance. All right, you have this in Canvas. Oh, did anybody want a paper copy of this?
Yeah.
Yes? They're colored. this is on the document, or colored on the document. Anybody else want to paper copy, whatever you can? No. We've seen this before when we did stars as a general. All stars are born in the cradle of life that is called a stellar nebula. All of them. I don't care how big they are. That is their nursery. You know, ones like ours are going to take the top route. And they're going to undergo main sequence for approximately 10 billion years. I'll come back and give you these numbers because you need to know them. The bigger the star, the quicker it dies. Just like the bigger the dog, the shorter the lifespan. Sad, it's true. After main sequence, when they start making carbon, they swell. And in the process of converting that helium to carbon, they are a red giant. Well, the surface of our sun will be past that of Mars, and it's going to eat all of the planets, just like a giant evil Pac-Man. Not that it's going to actually do that. It'd be cool if it did. Then, once it's getting ready to burn through the last of that helium, it collapses upon itself. It does not black hole. It did not blow up. It just retreats on itself, and it turns into something that's a little bit smaller than the size of our planet right now, called a white dwarf, which is a gently glowing diamond for the rest of its life. Maybe black dwarfs, but we're not sure. Now, the other alternative is if it's a big star. They're going to take this bottom route. And these guys still undergo main sequence for the bulk of their life, but they have a whole bunch of bloating expansions. So they're going to supergiant, and that's going to be in the process of making carbon, then further making neon, then further making oxygen, then further making silicon. And then honestly, they pretty much end at iron and sometimes make nickel. When they start making iron, they start auto-cannibalizing. It means they eat themselves from within. They explode. The smaller version's neutron star. Eventually, a neutron star will collapse into a smaller stellar black hole. But the ones that immediately black hole are at least 3 times the size of our sun. And all of these numbers that I just spout out are built into the notes. But you guys have this picture. You guys have this picture too. This is for our sun, our special hydrogen bomb in the sky. Our sun is right here. It's about 4.5 billion years old. And it's going to be productive.
Wait, how do you know it's 4.5 billion years old?
All the different types of spectrometry, the machines that look for chemical signatures, that's how we know by color and whatnot, what part of the life cycle the star is in, and it's actually burning. Each have their own like a color spectrum. And then we take a look at other stars and we use that to come analyze our. Now, can we like go back in time 4.5 billion years and watch this? No. May they be off by a few hundred million years? Yes. Okay, but this is what is the most widely accepted. And we're smack dab right here. And for about the next 3 billion years, Earth is probably going to be okay. And then our sun is going to start expanding, which is bad. Maybe good for Mars, but not good for us. And then right here is where it's going to eat us. And at its red giant stage, it'll swell to 2 astronomical units. The surface of our sun will be past that of Mars. Not quite to the asteroid belt. I'd have to pull out my cheat sheet. I can't remember exactly how many AUs out the asteroid belt is. Somewhere I've got a data table that puts all this information together for me. I can't remember myself. May I leave a message? I can't answer that right now. I got to try to get this house sold, and they're like blowing my phone up. So then our star will collapse down into a shell of its original volume. It still has all that mass, so it's extremely dense. Then it'll be a white dwarf for what we know forever. Most of the stars that you see, our sun is right here, right smack dab in the middle of main sequence, which is good for life. We won't be here in 3 billion years.
Yeah.
Anybody still need this? You guys do have this picture. If you're looking for the size, I have a slide later on that puts all three of them together, like deciding what it turns into and how many stellar masses it is. One of my classes asked me, I just sort of clean everything up and put it on one slide. All right, most stars, almost everything that you see in the night sky is either going to become a white dwarf or it already is a white dwarf. 95% of all stars, they end their life as carbon. There is no coincidence that we are primarily carbon-based life. In fact, to our knowledge, all life is carbon-based life. Because almost every star converts that original hydrogen from the Big Bang into carbon, and oxygen is sort of like an extra mutation. Like I said, mutation doesn't mean bad, it just means different. Give or take, main sequence is productive for 8 billion years. I'm going to change this to you, and I have a different slide in the powers of 10 just to make it easier on you. But the bigger the star, the more massive the star, not the radius, the mass, the actual kilograms, the matter that makes it up, the quicker it's going to die. Now, like I said, and we've mentioned this before, we do theorize that eventually this shining diamond that we call a white dwarf will lose the ability to give off all parts of the EM spectrum. And it's almost like turning off the light bulb. It's still there, it still has mass, it still has gravitational pull, we can still see its effect on other objects as it goes around it, it still acts like a star, it just doesn't make light, which is a black dwarf. But it's theorized that those things are so old, and our universe, to our knowledge, is only 13.8 billion years old because we can't see any further back in time. There just hasn't been enough time to create a black dwarf. So that's why it's called theoretical. And tomorrow we get to do time travel and relativity. I don't know how much of the antimatter stuff I can bring this to. Besides, I'm not doing calculus. Sorry, I'm just not. So the other 5% of all stars are the big ones, massives and supermassives, and sort of lump them together. These are the ones that go boom. They supernova. And if they're the smaller version, the neutron star, they're extremely dangerous. They vaporize all different kinds of stuff with their twin jets of gamma radiation that are pulsing out both sides like a giant laser beam of death. Or they create a black hole of which nothing can escape and everything gets sucked into it if we get close enough. These things die much faster than the little stars do. I said the bigger they are, the faster they burn up their fuel. And I don't mean fire, it's plasma. It's the same concept as a fire that's burning. What breaks Newtonian physics is this right here. You take all of that mass, like the largest known star is 265 times the mass of our star. It's called R136A1. We'll talk about that in a minute. It is the most massive known star in our galaxy. And the stars that we're going to talk about are specifically galaxy stars. Our galaxy, Milky Way. So you can take this supermassive red giant, which is 265 times the mass of our star, and it collapses into a point which has no volume, but still has all of that mass, or at least the bulk of it, because they do eject a bunch of the heavy elements when they explode. Dividing and multiplying by zero breaks normal physics. Newtonian physics, not quantum physics, not like when you see what looks like an equation that's across the entire blackboard, like the entire thing. I'm not talking about that kind of stuff. Regular old Newtonian physics cannot explain black holes. And we will talk much more about black holes tomorrow. Today just sort of leads into it because black holes are created by the death of supermassive stars. This is how you abbreviate 3 solar masses. Notice what this weird thing is down here. Black holes are birthed immediately from a star that has died that is at least 3 times the mass of our sun, which is 3 solar masses. The little circle with a dot in it means stars. Specifically our star. Because we base everything off of us because we said so, because humans are better than everything else. So it says us. until we get visited by intelligent life, and then we're in big trouble.
Okay, where you tinfoil?
Where did tinfoil that? Did you use look at this one? Neutron stars. These come from the massives. They blow up, but there's a bit that's left over that actually has volume. You're taking something that's almost 3 times the mass of our sun, and you're crushing it into the space of Manhattan. That's a neutron star. It's neutrons. So there's so much pressure that's going on inside these things that anything that had electrons, they have been fused down into their protons, because protons and electrons match with atoms. But these things smush them together until they fuse into the next thing up, a neutron, which is actually another mutation. Now, they do eventually collapse again and create the smallest of the stellar black holes. It just takes a lot of time. And in the process, before that happens, you've got these twin jets of gamma radiation, these pulses that are coming out, and as they spin, it's literally a death ray. Anywhere that thing touches, it will kill everything, vaporize everything in its path. We call them pulsars. The pulsar's evil big brother is a quasar. Those are related to black holes. Those are the brightest things in the sky. We're going to talk about the 4 major categories of black holes. I guess it's more of a focus on underneath the finish my notes that I lost some that I moved. I lost my most current data on it. But the way that I've taught this before is there are 3 major categories of black holes. And every year I've taught space, there are 3 major categories of black holes. The most common are called stellar, that normally have, and that's just the word normally, somewhere a mass between 3 and 10 suns. There are, on both sides, but most of them fall into this range. And they come from the death of a star, therefore they are a stellar black hole. These are the most common types of black holes. They're everywhere in our galaxy. The big one in the middle is not this type. The big one in the middle is a supermassive. That comes from gravitational collapse. That's different. So there's thousands, hundreds of thousands of these that pepper all throughout the Milky Way galaxy. And as long as we don't get too close to them, we're fine. We're not worried about the black holes that we know about. We're worried about the ones that we don't know about, especially if they're mobile, if they are rogue, which means they can be traveling, not just spinning like the rest of us in this nice little dance around our big black hole. They're actually wanderers. It could come up behind you and everything's gone and you didn't even realize it. Or at least we theorize, because it's not like we got a pet black hole somewhere. Intermediates, the next step up. These are the second most common types of black holes. And there's a bit of a gap in between these two. This is what happens when black holes cannibalize each other. They eat each other. And the bigger black hole is going to win.
Like the body?
I don't know. So the next galaxy over, Andromeda, that's on a collision course with us, its black hole is theorized to have somewhere between 110 million times the mass of our sun, up to 250 million times the mass of our sun. It has a nice, big, healthy, active central black hole. Whereas our black hole, Sagittarius A, is only about 4 million times the mass of our star. So even on the short end of this, it's almost 30 times the size of ours, if not more, because we have this nice big range. So that means when we merge, its black hole is going to consume our black hole. It's going to grow anywhere up to 4 million times the mass of our sun. In the process, it will emit a bunch of stuff. The two galaxies will collide, and it will actually awaken our galaxy back up, because our galaxy is in the process of dying. This is the new category that I didn't even know about until I double checked this yesterday, because black hole knowledge is changing rapidly. During the Big Bang, a whole bunch of teeny tiny, itty bitty black holes were birthed, some as small as atoms, and this is a miniature subclass. This one is new. I need to research this for tomorrow. I don't know how much time I'm going to have, but this is just a different subcategory. Somebody asked me what happened if you had a black hole the size of an atom next to you. Would you notice it? I don't know. I haven't double checked it yet. Honestly, it's theoretical. And then this one that we do know about, supermasses. These are the ones that are at the center of every known galaxy and holds them together. Ours is called Sagittarius A star. It has the mass of just over 4 million suns. I say suns, our sun. They are what is called gravitational collapse. So after the Big Bang, we had all this cosmic dust. We had these protons that were hooking up these electrons and making hydrogen, both regular hydrogen and anti-hydrogen. But we had these perfectly spherical, of course this is how the theory goes, these perfectly spherical cosmic dust sections where everything was perfectly pulled towards the center equally, all simultaneously, never birthed stars, and made ultramassive black holes like ton 618. That, to my knowledge, is still the largest mass black hole in existence. I bet you that has changed in the last 2 years. I need to double check it. Like I said, this stuff is changing. Now we can see the event horizon thanks to that 26-year-old mathematician analyzed, like, I can't tell you, like, the cloud can't even hold how much data she analyzed to get that image. I just need to pull that back into my black hole notes too. You have this cross-section? We took a cross-section of a supermassive star right when it was getting ready to supernova. This is what we would see. The outer layer, so we're going from its birth to its death, outside in. So we would have protostar. We have main sequence. Hydrogen and helium will take up the bulk of this thing's life. Helium, the carbon, is going to be the second. This is where the first expansion occurs in the supermassive. Once we primarily change it to carbon, these things ramp everything up and they go to the next element, which is neon. It is carbon fuses to neon. Magnesium is like excess, that's a little bit is made. It's a mutation. Once we're mostly neon, it goes up further, creates oxygen. Each time we have a fusion change, we have an expansion of the star. And we have a color change for that matter too. Which is part of the reason why we know how old these things get to be. It's by what they're churning out. Once we're primarily oxygen, we start making it to silicon. We have another expansion. I bet you that is going the other way. And then once we start making iron, drag that out of the way. This is where the star is dead, doesn't even know it. It has created a singularity in the center of it. And it is starting to eat itself from the inside out in the form of a black hole. Now, once it gets to a certain point, spreading out towards the surface, you have the actual explosion that you think of as a supernova. And while we have a supernova, all of the heavy, heavy elements are being produced because a star stops here at iron and nickel. And honestly, there is no coincidence as to why the thing that we are walking on, all of the terrestrials are primarily made out of iron and nickel. Yes, there are other silicates, but the core of the planet itself is iron and nickel because of that. Any element that's above these, they're made in supernova. Or we have crazy scientists that are actually making them in the lab, and they exist for like a fraction of a second before they're gone. Supernovas are where they have things like gold, silver, the precious metals, the heavy metals. The star has to actually explode, which has even more energy, which has even more fusion to produce the larger elements. So when people say you're made of stardust, you're literally made of stardust. It just has to coalesce in some way, somehow, turn into you. Because you are what you eat. Like the things that you consume replace the cells in your body and on your skin that you shut off. Okay, so this is what I just mentioned. At the point we're making iron, we have the death of the star. Now that death can mean different things. Yes, we have a supernova. It could be maybe a baby step as a neutron star and then a black hole, or it could leapfrog back and go directly to a black hole. So once again, these are for your massives and your supermassives. Average stars do not blow up. They expand, they eat their inner planets, they go back down to a white dwarf, and they leave all that planetary debris behind. Like a Pac-Man from, I don't even know. And to our knowledge, they stay a white dwarf forever just because we haven't seen a white dwarf. I will, when I do this little theoretical chunk that I have, this is a third of it. I always do my research and try to make sure that what I'm presenting to you is the most up-to-date released information. I have to stress that, released information, that is our way. And not go into quantum physics. It's cool that I don't have the calculus for it. All right. So somebody said they were like lifespan and how big and blah, blah, blah. Okay, so average stars, they white dwarf. They come from stars, which is the space, up to 1.4 solar masses. Massive stars, will neutron star, and they are born from stars that die somewhere between 1.4 and 3 solar masses. And then supermassive stars are the ones that are going to instantly black hole. They skip the neutron star part, and they come from stars that are larger than 3 solar masses. Once again, the circle with the dot and the M in front of it is a solar mass. That's how we abbreviate. I'm not changing it because this is where you guys, if you weren't picking it up as we were doing it, this is what you needed to know. Their size. Now, the longest lived are going to be your average star. And as you get larger, they die off faster. I'm actually really good on time. We went all the way to the bell in 6, but we got, the COVID thing took up like 10 minutes. You don't have this one? No. Okay. The circle, like 3, and then the M is mass, and the circle is solar. So 3 solar masses is how you translate that. It's just how we write it. Are you ready? All right, this is a cross section of a white dwarf. You guys have this too. It's on here. There may or may not be hydrogen present. Most likely that there isn't, like hardly any at all. So if you are walking on the surface of a white dwarf, which you couldn't, but let's just pretend that you could, which you can't. You'd be walking on a really thin crust of helium, but the bulk of it is literally a diamond. It is carbon with a little bit of oxygen mixed in for good measure. They are literally glowing diamonds. And this is where the carbon comes for life. Now, how does it get from a white dwarf and spread out to other areas so that when the planets coalesce, that carbon is there to be able to support life, the carbon and the hydrogen and the nitrogen and everything else that makes amino acids, the phosphorus, the sulfur? They have to get spread out somehow. And it's theorized that along comes these black holes, chew them up, just like a demented Pac-Man, and then in the process of what's called Hawking radiation, spits these things out. And they get spread out, or even possibly in the process of a supernova, which really the supernova does everything that's firing up. But the black holes are sort of like the death bringers and the light bringers all at the same time. And we'll talk a little bit about Hawking radiation tomorrow. I'm not going to go into like the mathematics behind it. I'm sorry. And yes, named after Stephen Hawking. I got it. This in the wheelchair and the robot thing talked to him. Had electrodes implanted into his brain, so all he had to do was think and it would speak for him, which is really cool. But no, it doesn't matter what type of star, main sequence, which is the hydrogen and helium, is going to take up the bulk of the no such restriction. And that's not Alright, we are almost through. You guys don't have this in this. And it's really difficult to read, so I put on the next slide, and it was black and white. What it says, stellar nebula is birth. Main sequence is give or take 10 billion years. The bigger the sun in that, the faster that's going to happen. This is not the Earth. This represents the normal size of the star versus its red giant counterpart. That's how much they expand. The red giant, this is for an average star. Red giant phase is give or take 100 million years. When it starts collapsing and leaves the bits of the planet behind, the planetary nebula lasts for approximately 100,000 years. And then our sun is going to be smaller than the Earth when it's completely and totally done doing its thing, really for the rest of its life. So since you cannot read that, for an average star, this is its life cycle. I'm not going to go through this step by step for the massives and the supermassives, because we don't have enough time. Massives and supermassives do this too, it's just faster. Like a lot faster. So your main sequences, give or take, 10 billion years, because what's a few hundred million years to a star? So 10 billion years, it is going to red giant for approximately 100 million years. We're going down by like powers of 10 now, like lots of powers of 10. Then it's going to be a planetary nebula for about 100,000 years. We dropped a 10 to the second there. No, 10 to the third. 10 to the third is a drop here. And then it's going to wait for forever, to our knowledge. We honestly do not know any different. Now we need to talk about those three stars and the tokamak. I have a very short video, and I need to upload this into my Canvas because I forgot to record 6th period. I just forgot the button. This has been one of those days. Yes. All right. There are three specific stars that we're going to talk about that are within our galaxy. The first is UI Scuti. UI Scuti is on the Sagittarius band, just like we are, but it's a heck of a lot closer to that black hole. And obviously, it's far enough away, it's not being eaten. But it's much, much, much closer. This is the largest known in sheer size alone, not the most mass. Just the biggest, most bloated beast that we have in our galaxy. It used to be UI Canis Majoris. That was the biggest star that I remember when I was younger. This guy just won out within the last 10 years. In fact, the documentary that we're going to watch Friday on black holes, if I'm not mistaken, says that UI Canis Majoris was still the largest star, and it was at the time. It's just, like I said, this stuff changes. The largest in sheer mass is 265 times the mass of our sun, and it is called R136A1. These things with the numbers and the letters, especially this little guy, This is the instrument that detected it. I forget what EDLM stands for. I'd have to go and look it up, and I didn't have enough time to do it. And then the numbers and the letters behind that have to do where it was located. So the most massive star, it's actually smaller in radius than Sketty. The most massive star is an R136A1. It is a Wolf-Rayet star. It is the most luminous. It is the brightest star that we have found.
Is that why we think it's the biggest?
Well, size does have a lot to do with luminosity. It does. The smallest known star used to be, when I first built these notes about a decade ago, used to be OGLE122b, which was also a red dwarf. There are stars that are smaller than red dwarfs. Brown dwarfs, however, are not properly fusing hydrogen to helium, and so they're not counted in the same category as the stars are actually doing that. The smallest known star is just a teensy tiny bit smaller than Saturn. OGLE122b used to be just a little bit bigger than Jupiter. It's just, we found another one that was smaller. And I think that if there is one that's smaller than this, it is going to be down at brown dwarf status, which sort of kicks it out of the possibility of being the smallest true star. In fact, if they have less mass, a lot of times they turn into what's called a hot Jupiter, which is a gaseous giant. But we don't have enough time to go into all the other different types of stellar bodies that exist, and planetary bodies that exist for that matter. I had to cut it down to what is most pertinent to us. And I still, like I said, I get to spend all day tomorrow on black holes. I need to update my notes. They're not completely updated. I need to add in at least ton 618. But I bet you that's not the biggest black hole anymore. I guarantee you it's not the biggest known black hole anymore. It was for a very long time. I need to get the audio clip of the black holes merging for you guys, and I need to get the image of the event horizon for you guys. Those have not made it into my notes, but they will. This is called a tokamak fusion generator. Now, when I was younger, it was understood that we would never be able to do nuclear fusion here on Earth, that was the only place that happened, it was inside star. And then along came the Russians in the 60s, and they went, oh yeah? And they built the very first tokamak generator. Well, they started it in the 60s. I don't know how long it took them to actually get one that was properly churning out fusion. But these things are almost like giant hollowed out donuts made of metal. Like you could run around inside them. Like they're not as big as CERN. They're not as big as the super collider that we have, but it is a super collider in essence, where there's a vacuum inside of it, just like the vacuum of space. And there's no particles in there except for what they put in there, which is hydrogen. And they're taking at temperatures that are hotter than the sun. They are taking these hydrogens, slamming them into each other, and they're fusing into helium, and they actually are a fusion generator. Are they able to make the lights turn on and off kind of reactor? No. Those are fission reactors. The ones like, if you've seen The Simpsons with the cooling stack, that uses uranium-238, breaks apart, gives off energy, heats the water, makes steam, spins the turbine, stored as electricity, and voila, lights turn on and off. This is not going to be capable of doing that. But we're working on it. This may have a lot of implications for stellar travel, for like trying to control singularities, possibly wormhole, that kind of stuff. Do we have the ability to do that yet? Are they working on it? Let's just hope they don't like create a black hole and like eat the planet in the process.
Oh, that'd be fun.
That would be fun. Yeah, because I want to experience spaghettification feet first. That would be awesome. Well, we don't know. Actually, we don't know. Because if you go feet first, considering time stops, would you be perpetually stuck? We'll talk. It is 20. It's right. It's 2020. We're going to have a singularity wink into existence in the middle of my room. I do have something that I want to show you. It's very short. It has 2 of those 3 stars listed. So we start with Earth. This is the smallest of those stars. This is oxygen. That was smaller than our sun. This is the place on the sky. Beta is Alex, this is the twins. I can't remember what our first one. I'm sorry. Nigel was in a night also the lower left foot. This is our right. This used to be the largest star in the light. That's what you are. You want to study? It's not a large one. This one's cheating because this is a black hole too. It's not a true study. And the going in Mach 32, it would take 24 years to get out of this. I don't think you need to go much past Mach 6 now, especially students will pass out. The blood can't stay in her brain. That's so like fighter pilots in the Air Force, they have special compression suits that they have to wear to keep the blood from draining out of their brain or they'll pass out. Okay, I'm gonna stop the recording. Okay, let's stop the recording.